Let's see how we can make an approximation in our equilibrium calculations when we have large equilibrium constants. To do this, we will use the following problem. An aqueous solution is made up to have 0.1 molar nickel 2 plus and 1 molar ammonia. And the formation of a nickel amine complex has an equilibrium constant of 5.5 times 10 to the 8th. Since that's larger than 10 to the third, we can assume that this is a large equilibrium constant and that the reaction goes mostly to products. So let's just dive in and start trying to solve this problem. And the first thing we always need to do is to write an equilibrium reaction that's balanced, that represents the equilibrium we're talking about. So we know that we have nickel 2 plus aqueous, and we have ammonia aqueous, and we're told that that forms, so is in equilibrium with, a nickel amine complex that has a 1 to 6 stoichiometry, so 1 nickel to 6 ammonias. And so to balance this reaction, I'm going to need 6 ammonias on the reactant side. So that's my equilibrium reaction, and the equilibrium constant for that reaction is 5.5 times 10 to the 8th, telling me that I mostly have this in solution with a little bit of this left over. So I'm told that when I start with a 0.1 molar solution of the nickel and a 1.0 molar solution of the ammonia. I don't have any of the nickel amine to start with because I didn't put any of that in my beaker. So when I look at how do I get to equilibrium, I'm going to have to make some nickel amine. And so if I make X of this, to do that, I'm going to have to use up X nickel plus, because every nickel amine uses 1 nickel. So if I make X of these, I use X of these. And then I'm also going to have to use up 6X of the ammonia, because every one of these uses up 6 ammonias. So that's the change to get to equilibrium. And then at equilibrium, I'm going to have 0.1 minus X of this, 1 minus 6X of this, and X of this. So now we start thinking about whether we can make an approximation or not. And we know from the fact that our equilibrium constant is very, very large that X is going to be a big number. So I can't ignore X relative to 1, or even worse, I can't ignore X relative to 0.1. So I can't make any approximations about the value of X relative to my initial concentrations here. So I'm going to have to do a little bit more work to try to figure out a way to do this approximation. The trick here is to remember that it doesn't matter whether I start with all reactants or whether I start with all products. When I get to equilibrium, I am going to have the equilibrium ratio of reactants to products. That will always be the same, no matter whether I start with all reactants or start with all products. Therefore, I can imagine that this reaction goes to completion, and then I will have all products, and then I can let the reaction come back to equilibrium from the product side rather than from the reactant side. And so if I let this reaction go to completion, I need to do a limiting reagent problem. And I can see that I have 1 divided by 6 equivalents of ammonia. And so 1 divided by 6 equals equivalents of ammonia. And 1.1 divided by 1 is the same as 1/10 equivalents of nickel. And so I have less equivalents of nickel than I do ammonia. And so nickel is going to be my limiting reagent. So I'm going to use up all of the nickel, meaning that for this limiting reagent problem, my amount my X is going to be 0.1. So I'm going to use up all my nickel because that's the limiting reagent. And then that means that if X is 0.1, then I've used up 6 times X, or 0.6 of the 1 molar that I had to start with for the ammonia. And so I'm going to be left with 1 minus 0.6, which is equal to 0.4 of the ammonia. And every time I use up 0.1 of the nickel, I make 0.1 of the nickel amine. And so I'm going to end up with 0.1 of the nickel amine. So this will become my new initial conditions after having shifted the reaction to make as many products as I can possibly make from the amount of reactants that I have. So again, I'm going to imagine that the reaction goes to completion. Once the reaction goes to completion, these would be the values that I would have to start with. But I know that I'm not at equilibrium at this point because I have no nickel 2+. So now I need to come back to equilibrium by making nickel 2+, which means that I will make 6X ammonia and I will lose X of the nickel amine. So at equilibrium, I'm going to have X of the nickel 2+ ion. I'm going to have the 0.4 that I started with plus 6X of my ammonia, and I'm going to have the 0.1 that I started with minus X of the nickel amine complex. This may seem like a lot of work just to solve this equilibrium problem, but let's see what this has done for us. Now we have a value of X that is small, because X now represents the amount of reactants left in solution at equilibrium. And our equilibrium constant is large, which means we have a very small amount of reactants left in solution at equilibrium. So X is now a small number, and I can ignore X relative to 0.4 and X relative to 0.1. And so I can approximate my equilibrium concentrations as X, approximately 0.4 of the ammonia, and approximately 0.1 of the nickel ammonium complex. And this allows us to write a much simpler expression for our equilibrium constant. So note that the expression for K is the nickel amine complex concentration divided by the nickel 2+ concentration divided by the ammonia concentration, but that has to be raised to the 6th power. And that's equal to our equilibrium constant value, which is 5.5 times 10 to the 8th. So notice that if I had not been able to ignore the 6X in my equilibrium concentration of ammonia, that I would have had an equation in the 6th power of X. And that would have been impossible to solve algebraically without some computer-aided help. And so now, with this approximation, with the way in which we have set this problem up, I can substitute in my equilibrium concentrations for these concentrations, and I can see that I end up with 0.1 divided by X times 0.4 quantity to the 6th is equal to 5.5 times 10 to the 8th. And this is a much simpler problem to solve for X. So to solve for X, I am going to flip both sides of this equation over. So I'm going to have 0.4 raised to the 6th times X divided by 0.1 is equal to 1 over 5.5 times 10 to the 8th. That I did because I wanted to get X in the numerator rather than in the denominator. And so now I can multiply both sides by 0.1 and divide both sides by 0.4 divided 0.4 to the 6th. And so I have X is equal to 0.1 divided by 0.4 raised to the 6th times 5.5 times 10 to the 8th. And that gives me 4.4 times 10 to the minus 8 molar. And so we can see that our approximation that X was very small compared to 0.4 or 0.1 was correct. And we can say that the nickel 2 plus concentration in solution is 4.4 times 10 to the minus 8, and that the ammonia concentration at equilibrium is approximately 0.4, and the nickel amine complex at equilibrium is approximately 0.1.